Hello, everybody. Welcome to today's lecture. So we finished up chapter 6 last time. So by now you've hopefully taken the chapter 6 exam or are going to soon, um, depending on when you watch this video. So we're going to move on now to chapter 2. So chapter 6 was all about graph theory. Now, as I've been saying, this class is not just about one type of math, right? Graph theory is one branch of math. But math has a lot of different branches that are seemingly unrelated from each other. When you really dive deep into them, you see that there are a lot of connections between them. But, on the surface, there's a lot of different branches of math that really have little to do with each other. So, you probably have already taken at some point in your life like algebra. I'm sure you've all taken like arithmetic, right? Like addition, subtraction, multiplication, division. And maybe even like fractions and stuff might fall under that category. And then after that, you start taking algebra. And then maybe you've seen like some geometry. And then, um, eventually you go on from there to take like trigonometry and calculus. So those are the ones most people are familiar with. But then there's some other areas of math like graph theory, which are lesser known, but just as important and just as studied. So the goal of this class is to introduce you to a whole bunch of different types of mathematics, specifically ones that will pertain more to like your interests as liberal arts students, because that's what we have here at Simmons is liberal arts majors like communication, religious studies, business, and sociology. These are all like liberal arts degrees, right? They're not like STEM degrees where we need to look at like college algebra and calculus and stuff like that. So, hopefully you enjoyed graph theory a little bit. I wouldn't say it's like I think it's an interesting field of math because it's very different from what we typically know, and it's easy to see some real life examples of where that can come up. And it's very relevant with things like the internet being all graph theory, because like the internet is a network in the graph theory sense. um so hopefully that was at least somewhat interesting. If it's not, you're in luck because we're going to start something completely new today. So whether or not you liked graph theory, we're pretty much just going to leave that behind now and start on something completely different. And that's kind of how this class is going to go. Once we're done with one topic, we're going to pack it up, move on to another topic that's completely different. And very few of these sections, if any, will have anything to do with the other sections. So we're going to leave graph theory in the past now, and we're going to move on to statistics. Okay. And that's also why we're having more exams than we normally would, is because we're having like kind of like mini exams. The chapter 6 one wasn't too long. I think it was like 10 questions or something. Which is shorter than an exam I would normally give. So, it's better to have exams at the end of every chapter rather than have like all of chapter 6 and part of chapter 2, because like I said, they're all self-contained. So that's why it's formatted this way. So we're going to start in chapter 2 today. If you look at chapter 2 in the book, you'll notice it's called Statistics Part 2. So why are we starting at Part 2? Well, part 1 isn't really, there's not really much math in it. It's mostly just definitions, and like a lot of like non-math things. And it's definitely worth reading through. It's like the kind of chapter that would be chapter 1 in any statistics book. So there's some like important key concepts from there, but it's not a lot of math, and we want to focus on the math. So it definitely would be worth like skimming through, and I'm going to pull some definitions from it to use in this chapter. That's why on the syllabus it says like chapter 2 and like in parentheses parts of chapter 1. But we're mainly just going to focus on the chapter 2 stuff, because that's where the math is, and that's the most important stuff for doing things like reading statistics, which is going to be very relevant for a lot of the fields you'll be going into, like sociology and business. You'll be reading statistics all the time, and really just in no matter what your major is, because we see statistics everywhere. We see them in the news all the time. Even on things like Facebook and stuff, people always are talking about statistics or sharing articles with statistics. So they're everywhere. They're hard to avoid. So we're gonna let me type in the section here. We're gonna look at 2.1 first. Sorry, give me one moment here. There we go. 2.1. All right. So there's a little paragraph before 2.1 that kind of gives you an introduction to this. So let's start there, actually. And I'll also introduce, well, first of all, probably the most important definition, what is statistics? Okay. So this is kind of paraphrasing from the chapter 1 of this book. Statistics is the branch of mathematics dealing with the collection, analysis, interpretation, and presentation of data. Okay. So statistics is the branch of mathematics dealing with the collection, analysis, interpretation, and presentation of data. So chapter 1 talks mostly about the collection part of the data. Okay. So that's a lot of the stuff that we're skipping. We're mostly going to talk about analysis of data, and somewhat interpretation of data. Typically for interpretation, you need to talk about probability, and with analysis too, which is chapter 3. So we're mostly going to, we're not going to be using any of that stuff because we haven't looked at probability yet. Presentation of data, this would be like, do you use like a bar graph? Do you use a pie chart? Do you use a line graph? How should we present the data, right? What are the key characteristics of the data we should present? Like, should we look at the average? Stuff like that. That's in chapter 1 a little bit and in chapter 2 a little bit, so we will see some of that. And a big thing about statistics is that it's a branch of math, right? But it is also like very different than a lot of areas of math. In fact, some of the bigger universities, they separate the math department and the statistics department, and they offer degrees in math and degrees in statistics, right? So it's kind of like different enough that some departments deal with it completely separately, but it is still a branch of math. The reason it's so different is that it uses what's called inductive reasoning. I think this definition is in chapter 1. You don't have to know the definitions. I'm just showing you why statistics is like how it's different from other branches of math. Inductive reasoning is where you go from something specific and you generalize it. So you go from specific to general. So in our case, we would take like a sample of something and we would study the sample. So say like we survey a bunch of people about their favorite colors. And then we would use that data and try to generalize it to like the rest of the country or something like that. right? So we start with something specific, and then we try to generalize it. Deductive reasoning is the opposite of that. You start with something general, and then you deal with specific examples from there. Okay, most of math is deductive reasoning, but statistics is inductive reasoning. And going from specific to general, it can be dangerous, right? Because not everything generalizes perfectly. So that's why we need to make sure we're doing it properly. And you're usually not saying that something is 100% true. You're usually saying it's within a certain probability of percent true. If you ever look at like statistics in like on the news or something like that, especially as like the presidential elections are coming up, you'll often see like poll numbers, right? Like this many people are voting for this, or say they're going to vote for this candidate. This many people say they're going to vote for this candidate. When they do that, they're not asking everybody in the country, right? They're asking a sample of the country, and then they're trying to generalize it to the entire country. So you'll see at the bottom of their charts, usually in like small text, margin of error plus or minus 1.5% or something like that. Okay, so they're saying, they're basically saying this is probably true. This is how sure we are. We can't ever say that something's 100% true when we're doing inductive reasoning. With deductive reasoning, you can. So that's what we're dealing with here. In chapter 2 specifically, we are dealing with the branch of statistics called numerical descriptive statistics. Okay. So these are, whoops. Numbers calculated from the sample and are used to describe or estimate population parameter. Okay. All right. So there's a few things we need to break down from this definition because it's using some of the language of chapter 1. So I'll point out some of the key words here. But the idea is, first of all, the things we're looking at are numerical, right? Statistics doesn't always have to be numerical. In the example I gave, like a survey about people's favorite colors, right? Our data there are colors. So it's going to be like blue, green, orange, red, whatever. They're not numbers, right? So the things we're looking at are going to be numbers. They're going to be numerical. Second, descriptive. It means that we're merely going to be describing the data. We're not going to be drawing conclusions based on the data. Okay. Usually to draw conclusions based on it, that's where you have to talk about like probability and stuff first. So we're just going to be looking at things that describe the data. So like, okay, here's the data. What's the average? What's the median? What's the range of the data? Stuff like that. So there's a few keywords we need to talk about here. One is sample. Whoops, I didn't know that was going to happen. One is sample. Okay. Let me highlight in red here. Sample, population, and parameter. Okay. These are 3 words we really need to define carefully before we really talk about them. So we'll come back to this definition after we do that. So first of all, let's look at a sample versus a population. Okay. So the population, when we're talking about the population in statistics, when we normally talk about population, we're talking about like the amount of people living in an area or something like that, right? Or maybe the amount of like animals living in an area. But what we want to know, what we're using the word population to mean is basically the entire, let me get the exact wording here because I don't want to butcher this because it's an important word. So I'm just going to pull this from chapter 1. All right. So it's a set of measurements or observations from all objects under study. Okay. In other words, well, here, let's just talk about it before I try to reword it. So what do we mean by this? A set of measurements or observations from all objects under study. So typically when we're talking about statistics, we're trying to measure something or we're trying to observe something. So like an observation could be like somebody's favorite color, right? Like we're like observing what their favorite color is. Measurement could be like we're measuring the length of something, or it could just be like how long did something take to do, things like that. The important thing though here is that it's from all objects under study. So population is like the entirety of what we could be studying. If we're talking about who we think that, if we're talking about like the predicted presidential candidate, for example, and we're surveying people about who they're going to vote for, the population would be the votes from every single person that can vote in the country. Okay. So it's the entirety of what we can draw on. The sample is what we actually look at, right? So the sample is going to be the group and the measurements that we actually look at. The population is the group and the measurements that we could have looked at. So the entirety of it. So the population's the entire thing. The sample is part of the thing, right? So this is just a subset of the population. Okay. So, for example, population could be like the test scores. So here's an example. Population could be the test scores from every section of Math 101. Whereas a sample would be the test scores from this section of Math 101. Okay. So population is the entire thing that we could look at. Sample is, okay, this is what we're actually going to look at. And typically we want to use the sample in order to make predictions about the population, because a lot of times the population is too big for us to study the entire thing, right? If like a news organization wants to do a study about who they believe is going to win the presidential election, they can't ask every single person, right? It just wouldn't be feasible. So they only ask a sample of people, right? They ask however many people they determine is big enough. They ask that many people, and then they use that to guess what the how the population is going to vote. So the sample is included in the population. The population is bigger than the sample. Okay. Now, the other word, parameter, parameter and a statistic okay. So a statistic is essentially like a number that is pulled from the sample, whereas a parameter is a number that's pulled from the population. Okay, so they're the same thing. It just depends on where you get it from. Again, let me find the exact wording here because it is important. Yeah. Okay. So these are both like numerical values. This is just a numerical value calculated from a population. And then the statistic is a numerical value calculated from a sample. Okay. And this is typically used to estimate the parameter. So normally when we're talking about this stuff, we talk about statistics because we're talking about like, okay, the percent of people whose favorite color is blue. Well, we're only talking actually about the percent of people from the surveys that we did. We're just using that to estimate the parameter. The parameter would be the actual percentage of people in the country whose favorite color is blue. There's no possible way for us to know that. So instead, we are predicting what it is based on our statistic. So parameters, we typically can't know what that is unless we have like a small population or unless like the problem gives it to us. So we typically are using a statistic, and that's something that we can find on our own, and then we can use that to estimate what the parameter would be. Okay. So these are the same thing. It's just that the statistic is pulled from the sample and the parameter is pulled from the population. So as an example with the test scores, if the test score from every section of Math 101, if the average test score was an 80, but the average test score from the sample was an 85, the 85 would be the statistic, the 80 would be the parameter, and then we would use the 85 to estimate what the parameter is. So we'd probably do it incorrectly there, right? But I mean, that's how it goes. So going back here, numerical descriptive statistics, these are numbers calculated from the sample, right? So that's why it's called a statistic, and are used to describe or estimate the population parameter. So population parameter is a little redundant. Parameters are always from the population, but just so you don't have to remember that, it's often called a population parameter, or we'll often call a statistic a sample statistic, just so you don't have to remember which one it goes with. Then you really only have to remember the difference between sample and population. So these are just, it's basically just the same definition of statistic here. It's just specifying that it's numerical, and specifying that it's describing. I have a typo here. What was that supposed to be? Describe or estimate, not of estimate. Or estimate. Okay. All right, so these are some preliminary definitions. Let's jump into a little bit more like math now. What this section actually is called, 2.1. Come on. Okay, so 2.1 is actually called proportion. So this is like a basic starting statistic that we often would want to calculate. Okay. Proportion. So this could be, for example, okay, going back to the test scores, what's the proportion of people who got an A? What's the proportion of people who got a B, etc.? So hopefully you've dealt with proportions at some point. If you've taken Math 099, developmental math, you've seen them there. Maybe you don't remember it being called this, but it's just essentially like a fraction, right? So a proportion, the definition of this it's a measurement of how often something occurs in relation to the total. Okay. So this is like my own definition because there's not really a definition of it in the book. There's really just a formula for it. So measurement of how often something occurs in relation to the total occurrences, I should say. So that makes more sense. Occur, I don't know if there's 2 R's or 1 R. So I'm sorry if I spelled this wrong. Occurrences. So for example, with the test scores, if say, let's say the test scores broke down like this. So we have our grade and the number of people who scored this grade. So let's say we have like 10 A's, 8 B's. Whoops, it's backwards. 8 B's, 7 C's, and let's go 5 C's, 2 D's, and 6 F's. Okay. So if we want to know the proportion of A's, well, let's think back to like fractions. How would we make this make sense? How many people got A's in relation to the total amount of people taking the test? Okay. So 10 people got A's, and we would write this as 10 out of how many total people took the test. And then to find that, we can just add up all the grades, right? So 10 plus 8 plus 5 plus 2 plus 6. So we get 18, 23, 25, 31. So we get 10 over 31. So this is the proportion of A's, 10 over 31. And you could write that as a percentage if you want. You just turn the fraction into a percent. You could just do the division in your calculator and it'll give you the decimal form and then move the decimal over. So that's like some Math 099 stuff, which I'll show some examples of in some problems later. First, I want to write down the actual formula for this, right? So we just kind of reason through this, but what's like the real formula for it if, it's hard to reason through? Okay, so the formula let me write formulas. So oftentimes we're presented with two different types of this. We're presented with the parameter type and the statistic type. So how do you write it if you're calculating it from the population? And how do you write it if you're calculating it from the sample? And it's the same thing typically, but the notation used is differently. So I want to present both of them so that if you're ever reading about statistics, you can discern the difference between them. So the population proportion is typically written as P. Okay, so just a lowercase p equals R over N. Okay. Where P is the population, or is the population proportion, right? That's what we're calculating. R is the number of successes observed. So when we say success here, we mean it's counting towards whatever we're calculating. So a success with proportion of A's would be they got an A, right? If we were calculating the proportions of F's, then a success would be that they got an F. So the way we're using success here doesn't necessarily mean like the best possible outcome. It means it counts towards whatever we're trying to measure. Okay. So R is the number of successes, and capital N is the it's the population. Okay. So we have P equals R over N. So here we did 10 was our number of successes, N was 31 because that's the total number of people who took the exam. Okay. A little side note here. We always use N, big N, for population size. And little n for sample size. Okay. So if you're ever reading a study, typically it'll have like n equals 300 or something like that somewhere in the article title, because that will tell you exactly how many people they did the study on. Okay, so this tells you how big their sample was. Big N, we typically don't even know what it is because it's hard to know the exact number of the population. It depends on the context. Like with test scores, then yeah, we probably would know. But with like total number of eligible voters in the US, for example, that's a number that's always changing, so it's hard to really know exactly what it is. You'll also see typically we use Greek letters for parameters, and we use R letters for samples. This is kind of an anti-example of that because we're using R letter for the population, but typically we use Greek letters for the population, which we'll see later. Okay. So for the sample proportion, it's calculated the exact same way. It's just they use different notation for it, so I just want to write both of them. But the process is the same. You're just taking whatever it is you're trying to observe and dividing it by the total. Okay. That's all we're doing here. So don't get bogged down in the formula if it's confusing or in the notation. So the sample proportion is P with this little caret symbol over it, which we call P hat, equals R over N. So really the only difference here is that we're using little n instead of big N because we're calculating it from the sample instead of from the population. Okay, so that's the only difference. And then we use a different letter so that, we know these aren't exactly the same thing. So P hat is read as P hat. Okay, but they're the exact same things. So P hat. And yeah, there's literally no difference though. So let's look at this example that they have here. Example 2.1.1. So it says, suppose that you ask 140 people if they prefer vanilla ice cream to other flavors, and 86 say yes. Okay. What is the proportion of people who prefer vanilla? Okay. So, first of all, this is a sample, right? Because we're only asking 140 people. So what the population is depends on the context, but let's say we're trying to figure out what the preferred ice cream flavor of people in Louisville is. Okay. The population would be the preferred ice cream flavor of people in Louisville. The sample is the preferred ice cream flavor of these 140 people. Either way, this isn't going to be a population. This is going to be a sample. For our purposes, it really doesn't make a difference. In fact, there's only going to be really one formula that actually is different based on the sample and the population. But typically it's not going to matter. So again, don't get bogged down in the notation or the formula if it's confusing. Just think about what we're asking here and what we should do. The proportion of people who prefer vanilla. Well, we know 86 of them prefer vanilla, right? And we want to divide that by the total number of people, which here is 140. Okay. So, and this would technically be p hat because it's a sample, but again, don't get bogged down in that if it's confusing. So this is, if you put this in your calculator, you're going to get 0.614. We have to round it a little bit here because it's a long decimal, which if you turn that into a percentage, remember all you need to do is move the decimal over twice. That's how we go from decimal to percent. So we get 61.4%. Okay. Now you can write it any of these ways that you want. Okay, you can write it like this. You can write it like this. You can write it like this. It's fine. I don't care which way you write it, but you do need to be familiar with all of these ways because you have to be able to interpret it if it's presented to you, right? So you need to know that you need to know how to work with the percentages just as well as the fractions, so that if the problem gives it to you in a percentage, you can still handle it. But when you're reporting your answer, you can just leave it as a fraction and then just be done with it. Okay. All right. Let's see. What are we looking at in time? 41 minutes. Another question we could ask, which isn't presented in the book. Okay. Another question. Or not how many, rather, what is the proportion of people who do not prefer vanilla? Okay. Because we only have two options here, we can figure this out. Right? If 86 people say they do prefer vanilla and there's 140 people total, then whatever's left must have said they do not prefer vanilla. So we could do that as 140 minus 86 divided by 140. Right? So this would be p hat again. So it's whatever's left over, right? If 86 said yes, the rest of them had to have said no. The way we find that would be 140 minus 86. So we'll just put that in a calculator here. So we get 54 people do not prefer vanilla, which if we do the division is about 0.386, which is 38.6%. Now, the reason I want to point this out is because notice we have two options here, right? You either prefer vanilla or you don't. So this percentage, the proportion of people who said yes, and this percentage, the proportion of people who say no, should add up to 100% because those are only two options, and they do, right? You can add these together and they'll be at 100%. Depending on how you round, it might be like 99.9 or 100.1, but it should be really close to 100%. Okay. All right. I think we'll stop there for today with 2.1, but we did a little more than that too, like some of the definitions from chapter 1. So next time we'll look at 2.2, where we're going to talk about average and the difference between mean, median, and mode. And then if we have time, we'll go on to 2.3. Okay. Another thing we'll talk about next time is the difference between a qualitative and a quantitative variable. I'm just going to briefly mention them because that's again from chapter 1. So I encourage you to look at chapter 1 and look at the difference between a quantitative and a qualitative variable. Okay. Also, feel free to go look at the chapter 1 stuff about the sample and population and the statistics versus the parameter as well. Okay. It's all laid out there in chapter 1. But definitely make sure you look at the difference between qualitative and quantitative because I'm not going to spend a lot of time on it. Okay. All right. So yeah, that's it for today though. So thank you for watching and have a great day. I'll see you next time.